and we'll get started with just the four of us, three of you and me. Yep, that's all we've got. Let me make sure nobody is still waiting. Not yet. So hopefully they'll be coming. I usually say this further into the class, but I'll just ask it now. I hope that all of you who are registered to vote have voted. If you haven't, because this class technically goes to 7:45, I would rather you go vote and come back and pick up the class, because I am recording the class. Everything will be recorded. It'll be there. So if you haven't voted, please vote, okay? But it's completely up to you. It's just an important right and privilege. And when they brag about they've got 47% of the registered voters voted, that means that we just elected someone with maybe 24% of the electorate of the people eligible to vote just elected our leader. Okay, wait a minute, that's not a democracy. That's a sham. Almost. But anyway, let's go on from there. I was hoping more would show up. That's one reason I'm sort of babbling on. But since we don't have anyone else here in the wings so far, let's go on and pick up where we left off last time. Now, I don't think there's anyone behind that, but I'm going to check one more time. Nope, still got 3 students and me. Okay. If there's no questions on what we've done so far, we're in Chapter 3, Energy. Where we're going with this, we don't have that much more to go in the PowerPoints, but we weren't quite at the point for a PowerPoint yet, because we still have to do examples 3.9 and 3.10 on page 75. So that's where we're going to begin today. This is under the heading of energy conversion. So we're going to do a couple of problems with energy conversion. Then we're going to talk about energy conservation, which basically is related to that. And then several types of energy sources today and energy sources tomorrow. And that's going to wrap up Chapter 3. We're going to get started on Chapter 4. But today's lab, which we'll do starting at 5:45, will be an energy lab as well. Now, as I was telling some of you, maybe before all of you got here, I've been working on the lab for Thursday, and I had hoped to do a temperature lab, thermometry lab. I could not find a decent thermometer lab in the simulation. So we're going to have another energy lab on Thursday as well. We're doing one energy lab today. We had an energy skate park last time. We're doing, I can't remember the name of it this time, but it's another energy lab, and then we'll be doing a pendulum lab on Thursday. Then we'll do some things in thermometry and thermodynamics and that type of thing, but that'll be next week. So that's where we're heading. We're going to finish Chapter 3 and start Chapter 4, do another lab on Chapter 3, and then Thursday continue Chapter 4, but pick up yet another lab on Chapter 3. Now, in between all that, after today's class, if we do finish Chapter 3, which I think we will, I will be posting the Chapter 3 test after today's lab. So there's yet another test, so please sort of try to keep up with it. I think I already put something in the weekly activities, a column there or entry there for Chapter 3 test. However, I didn't post it yet. Whoever did the silly templates that we're having to follow didn't allow me a place to put it in. I mean, there's a place, but they didn't allow me a plus sign to put it there. So I will show you. It's going to go under the Blackboard messages. where I think the others have gone to. Sorry about that. I don't know why they didn't. I'll check again and make sure. I'm doing so many different classes, I can't remember for sure which one had it and which one didn't, but we'll check on that later. Okay, any questions? Where we're going, how we're going to get there, whatever. Okay, if not, we're, as I was mentioning before, in chapter 3, energy. We're in the section called energy conversion, and we're on page 75, very top of the left-hand column. It's a couple of examples. We'll do those first and then move on to energy conservation. So here's example 3.9, page 75. A 1.0 kilogram book falls from a height of 1.0 meter. Okay, now I had thought we had done this one last time, but evidently we did not. So let's, or my mark indicates we didn't. I can't get my pen to move. Now it did, there it goes. Okay, so 1.0 kilogram book. What is that a measure of? 1.0 kilograms. Mass of the book. Okay. It falls from a height of 1.0 meters. So the height from which it fell, 1.0 meters, and they sort of just gave away, that's the height. Okay. What is its velocity just as it hits the floor? What we're looking for is the velocity just at the floor. Okay, that's what we're looking for. Now, just on the previous page, page 74, very bottom of that right-hand column, they give you the formula we'll be using. Okay, and we figured out how they derived this. The velocity, right, the final velocity just before it hits the floor, I put VL for floor, but it's also a final velocity, is the square root of 2gh. That's all. Doesn't matter what the mass of the book was. All it matters is the height from which it fell and what was the acceleration due to gravity. So this entry here is completely non-usable here. You could go back and do it from scratch, and you could use this mass for potential energy and use it for kinetic energy, and they basically cancel each other out. So all we do is plug in the square root of 2 times the acceleration due to gravity. We're assuming it is on Earth, 9.8 meters per second squared, times height was 1.0 meters. Okay, now 2 has no units. That was just from the 1/2 in the velocity. That's where that 2 came from. So basically 2 times 9.8 is 19.6. Okay, that's the numerical part. The unit part is meters squared per second squared. Meters squared per second squared. Okay, and then you pull out your handy dandy calculators. Okay, I think I've got mine here. Let's see if it's charged. Not completely, but I'll charge it. And we'll go to the calculator mode here. We will need a square root, so I'll turn it sideways to get the scientific mode. And it's 19.6. I have to enter that first. If you have a fancy calculator, you might be able to enter the square root thing first. And then I press the square root thing, and I get something on the order of, not exact, but on the order of 4.4 And what the units? Take a square root of meter squared per second squared, you get meters per second, which is a great unit for a velocity. Now, I thought we had done that one before, but I don't know. I've taught this course so many times I can't keep up with it. But in the book, you'll notice they put the answer incorrectly. The 4.4 is fine, but they put meter seconds, not meters per second. So that should be a slash through it. Now, if some of you have newer books than I do, they may have gotten that corrected in the newer book. But if you don't, then you know, just go for it. Make the change meter per second. Now, I'm pretty sure we did this one too. What is the kinetic energy of a 1.0 kilogram book just before it hits the floor after a 1.0 meter fall? Okay, well, that's exactly what it was describing here, but they're asking what is its kinetic energy just before it hit. Now, oops, here comes Brianna. I was hoping somebody else was going to show up today. Not that I mind having just the three of you, but it seems such a shame to have a class that's supposed to have 16 people in it and have just 3. So Brianna is here. Wrong date. There we go. So that gets us up to 4 students and me. Basically, y'all have enough for a bridge table, and that's about it. Let me make sure nobody else is in the wings. Wait, that indicates only 5, and that's what we've got. So, Brianna, we just finished doing example 3.9 at the top of page 75, and I was just about to do 3.10. Oh, and here comes Tobias. Okay, so let me get Tobias here. Whoa. Okay, now we got enough for a basketball team. Co-ed, of course, but we can do that. Now, here's what they did that was, I think, a little crazy. Okay, they said, what is the kinetic energy of that 1 kilogram book just before it hits the floor after that 1.0 meter fall? Well, here's what they did. They said kinetic energy is equal to 1/2 mv squared. Now here we do need the mass for this part and for any part, and that would be 1/2 1.0 meters, I'm sorry, kilograms. That's the mass in 1.0 kilograms. That's pretty ugly, isn't it? Let me go back and make that more readable. 1.0 kilograms times velocity squared, and they took this thing and squared it. Now, here's what they should have done. I'll show you what they did. They took the 4.4 meters per second and squared it. Okay? Now, if you do that on your calculator, I'm not going to, but I'm going to do it. I'm going to square that whole big old number we had here before they rounded it off. Okay? And if you square that, you get your 19.6, which is under the radical. Then you multiply or take half of that because you're multiplying by 1 and dividing by 2. So divide by 2 and you get 9.8. That should be your answer. Okay? That should be approximately 9.8 joules. Now, if you notice what they did in the book, they gave you an answer of 9.7 joules. And here's where they got that. They did 4.4 after they rounded, squared that, and then took half of that. And that gave them 9.7. all they did was do a round-off error. They didn't need to do a round-off error. All they had to do was calculate the MGH here at the top of the, I can't get my pen to show up. Where is the pen? There it is. Okay. If you did MGH up here, which was 1 times 9.8 times 1, you would get 9.8 joules. That's the energy at the bottom. Kinetic energy at the bottom is the gravitational potential energy at the top. Without rounding off this answer here and then using the rounded answer to give you an answer that's too small. Okay, so I think they were just a little nuts there. All right, enough of my pontificating. I'm going to put my calculator back on charge here so I won't risk running out of charge by lab time, because we will be using it in the lab. Not I think we were going to lose much, but in case we did. All right, so let's go back to our PowerPoints. Okay, we're up to 5 students still. Yep. Where is everybody? I hope that means they're all voting. Okay, that I would sort of go along with. Okay. Now, I thought I already had this set up, but it doesn't seem to be set up. So let's go back and go from current slide again. Now, the energy conversion, we talked about this last time. Okay, so I'm just going to go through it quickly. There is the bowling ball energy conversion. Here is the pendulum energy conversion. That's the lab we'll be doing on Thursday. Okay, we'll already be through with chapter 3, I think, by then, and we will be still doing that lab, the pendulum lab. So that's going to be Thursday's lab. So we've already hit this, we've already dealt with it all. Let's move on to, and as in before, they say the energy of the pendulum is fixed, it's constant. That's the mechanical energy of the pendulum. And the mechanical energy is the sum of the kinetic energy and the potential energy. Whether you're up here at the top where it's all potential energy, down here at the bottom where it's all kinetic energy, or anywhere in between, the mechanical energy is constant. It just changes always from potential to kinetic to potential to kinetic to potential to kinetic. Always is changing, always. Okay, so that's energy conversion. Another example of that. All right, now on continuing on page 75, there is a blurb here about energy conservation. Now, this goes right along with energy conversion. I want to thumb through. I apologize ahead of time. I just noticed the cough and stuff. This past weekend, we were over in Georgia. When my parents died, they left the farm, split among the 4 of us. My other 3 siblings all live on the farm, and we have a place there that we can go and stay. And we went over to get some work done. It was a perfect weekend for burning a lot of we have 4 big old pecan trees, and they just lose limbs like crazy. So we had been stacking them up all summer because it was just too hot to do any burning then. So finally this weekend it was just perfect temperature and not that much wind, so we were able to burn huge stacks of old pecan limbs. Well, that irritated my throat, irritated my voice, irritated everything. Plus I was mowing a lot, which had lots of ragweed and goldenrod and just about everything else you could imagine, thistle and everything else. I had on a mask, but still probably didn't keep all that out. And then it also turned cooler, so I may have a little bit of a cold as well. And here is Rodrigo. So let me get him marked here. All this is saying, sorry that my voice is sort of scratchy. My throat is very, very scratchy, so every now and then I will have to stop and probably get something to soothe the voice a little bit. Okay, now my desk seems like it's about ready to fall up. Oh, and here comes Daniel. So let me get Daniel here. All right, middle part of the alphabet is really filling up nicely. The bottom's a bit sparse, and except for Angelita at the top, it's a bit sparse. So hopefully others will be coming in too. Okay. So here we're going to talk about energy conservation. For those who just got here, we're on page 75, chapter 3, energy, and page 75 is beginning energy conservation. We've just worked the last two examples in energy conversion and then moving on to energy conservation. I want to do a quick look ahead to see if I can't look ahead. This thing isn't allowing me to. Okay. Nope, it's not showing what I really wish they were showing. Okay, so I'm going to hold it up for you to see. For those of you who have books, it's one of the best illustrations of what we're talking about. But excuse me just a minute. Okay, sorry about that, but I want to make sure y'all were all awake still. Okay, now first, okay, we'll do this slide here because it's referring back to what we just did. Energy conservation. Energy is never, ever, ever created nor destroyed. Whatever energy is there, it's been there. It's going to be there. It's never created nor destroyed. It changes form like crazy. It can be converted, and this is why I think it belonged on the last slide. Can be converted from one form to another, but the total energy remains the same. One example of this is free fall. When you drop something from a high distance, all it has up there is potential energy, gravitational potential energy. As it falls, it gains kinetic energy but loses potential energy. Okay, but the total energy remains the same. Now, sure enough, when it's falling, it's meeting some air resistance. Now, that air resistance converts some of that energy into low-level heat. Okay, now that low-level heat is very, very, very difficult to get any usefulness out of it. It's not destroyed, but the usefulness is almost gone. Okay, so it's a little bit different concept than it's being destroyed. Its usefulness is just very little. Now, this free fall experiment is basically what we were just doing in that last the last two problems, really. The potential energy lost from free fall, when that's all the energy it has up here is potential energy. The potential energy lost as the object falls is gained as kinetic energy. Okay, on the upper side, that's mgh, that's potential energy at the top. The kinetic energy right before it hits the ground or the floor or the desk or whatever it's hitting there, that's 1/2 mv final squared, because that final velocity right before it hits, that's going to be your maximum kinetic energy. You've lost all your potential energy, that's going to be your kinetic energy. If you solve this for the V final, what we'll do is multiply 2 to both sides. That gives you 2 mgh is equal to mv final squared. Okay, we did this before. Then divide both sides by m, and your mass goes away. That's why it didn't matter at all what the mass was. Okay, That's why good old Aristotle's original observation that heavier objects fall faster than lighter objects, not necessarily the case. Galileo showed that not to be the case. Okay, so now we have V final squared is equal to 2GH. Take the square root of both sides, you get V final is equal to square root of 2GH. That's exactly what we used in that last example. All right, that being said, this is a table that's on page 74. Before we did the experiments we just did, let's say you originally had that ball at a height of 10 meters and it's being held constant right there at 10 meters. So all it has is potential energy, and that's mgh. Now the mass happens to be 1 kilogram. G is 9.8 meters per second squared. The height is 10 meters. That's at release. Now you're releasing this. You're not throwing it down. That would give it an initial velocity. You're releasing it from rest, so therefore its initial velocity is 0. Okay? So the velocity being 0, your kinetic energy is also 0. As it falls, when it gets to half its height, 5 meters, it's lost half of its potential energy. That was not lost completely. It gained exactly that 49 joules that it lost. It gained as kinetic energy. Now the velocity is up to 9.9 meters per second. Okay, you can use this formula to do there. Your h was now 5 meters, 2 times g times h. That would be 9. That's 98. And the square root of 98 is right at 9.9 meters per second. Then just before it hits, when its potential energy goes to 0, the velocity there is, and this will be the final velocity here, 2gh. So 2 times 9.8 is 19.6 times the height that it fell was 10 meters, so that would be 96, and the square root of 96, is that right? I'm doing it in my head, and my head's clogged up. Okay. 2 times 9.8 times 2 times 9.8 times 10 equal 196, and take a square root of that and you get 14. 14 meters per second would be your velocity right at the bottom. Okay, square root of 2gh. All right, now before we get to this next slide, here's one that I think is even better. And I'm going to hold the book up for you. I can't hold it long, it's too heavy of a book, but if you got your book, that is a really good descriptive slide. Okay, I'm going to start at the upper right here and work my way around it. Okay, it just shows how energy is conserved as it moves from one moon to the other. Just about all the energy we have right now basically is coming from nuclear energy. Now you say, wait a minute, we don't have that many nuclear energy plants. The energy came from nuclear energy. Some of that nuclear energy was happening millennia ago, thousands of years ago, okay? Because you see, the sun, our major source of energy, is a constant nuclear reaction. A fusion reaction, those that were in the class earlier, Angelita and Jacob, when you had Physical Science 111, you know that that energy from the sun and all the stars are nuclear energy pretty much. There's other forms there too, but it's mostly nuclear. Okay, now that radiation coming from the nuclear fusion, and they list several other kinds here too. We do have nuclear power plants here on the Earth. They produce a certain amount of energy, pretty good energy. The trouble is what you do with the waste. That's the trouble with nuclear energy, and if there are problems. But most of that nuclear energy is relatively clean until you got to mess with the waste. Okay, the nuclear energy from the sun, from that massive nuclear fusion reaction that's going on constantly on the sun, it's heading out in all directions in space through radiation. Okay, they mention gamma radiation, but there's also X radiation. There's all this different kind of radiation going out into space. Our little bitty planet over here just gets a small fraction of that energy. Okay, that radiant energy comes in. Now fortunately, our atmosphere blocks most of the deadly harmful radiation, the gamma radiation, the X radiation, and including much of the ultraviolet radiation. Some ultraviolet gets through, and that causes problems. Skin cancers, cataracts, things like wrinkling of skin, those kinds of things. But that's radiant energy coming in. That light that comes in is a form of radiant energy. That's what the little green leaves on their trees and their grasses and shrubs and all that, they absorb that energy coming from the sun, which came from nuclear energy, came by way of radiant energy, made it through our atmosphere and activated the chlorophyll, worked with the chlorophyll and changed the carbon dioxide that it took out of the air, the water that it took out of the ground, and formed sugars. Okay, fructose, sucrose, glucose, simple sugars. And the trees proceeded. Right in our backyard we have a walnut tree there, 2 pecan trees, oak trees. You know, all those trees are changing that energy, that chemical energy, into walnuts, pecans, acorns, hackberry, whatever, and that is stored as stored chemical energy. Most of those are fat energy. Some of it is carbohydrate energy. The wood in the tree is a complex carbohydrate we call cellulose. All that energy is being stored by the trees or produced by the nuts in the trees, and anyway, that's being converted to that. So that is chemical energy. That's the top part. Photosynthesis is using the energy from the light, which came from the nuclear energy of the sun, by way of radiant energy in the atmosphere and in space, and photosynthesis is changing that to chemical energy. Let's go on around that direction then. Some of that chemical energy, if you are using batteries, that chemical energy goes to electrical energy. If you're that's called a battery fuel cell. Okay, from electrical energy, some more of that chemical energy goes down to the right lower corner to mechanical energy. That would be when you were operating a heat engine, as in driving your car, okay, or anything such as that. There's another energy conversion, chemical to mechanical. Let's go back to the electrical. Electric motor changes electrical energy into mechanical energy. That could be your lawnmower, your well, actually a lawnmower would be a heat engine unless it's electric lawnmower, and then that would be electrical energy. Okay, let's go back to the mechanical. If you the mechanical energy of, say, that motor or whatever is running, it produces heat. That heat energy is now changed back to radiant energy. So every one of these corners, nuclear, radiant, chemical, electrical, and mechanical, can go back and forth in both directions to any other corner. Okay? Just depends on how you got. The most loss that you have, even though it's not lost, it's that wasted heat energy that you can't really do a lot with. But that to me is one of the best diagrams you will ever see about the conversion of one energy form to another, to another, to another, to another, back and forth any way whatsoever. All right, now the right hand side of that column, the right hand column there, takes us to this one. And this is a very simple illustration of what we're just talking about. Nuclear energy from the sun travels through space and through our atmosphere as radiant energy, electromagnetic energy. That hits the little green trees, okay, or plants of any nature whatsoever. That stores the light energy from the sun into chemical energy in the plants, okay. That could be grass that the cattle would eat. We then later eat the cattle, and then, or the chickens or the pigs or whatever. That is, ultimately, they get their food source from the plants. That could be grains like corn or wheat or oats or rye or barley or something like that. Or it could be fruit on the trees. We eat the stored chemical energy. We use that chemical energy to ride our bikes, to do our walking, to mow our grass, to whatever we're doing. That chemical energy is then converted to mechanical energy, the energy of motion and storage. In time, most of that is wasted as heat energy. But that radiant energy goes back into the atmosphere, warms up the atmosphere, and there we have the whole process going for full circle. Now, it doesn't show everything here, but it shows a lot of that process that was shown in the other diagram. That's called the flow of energy. Energy, again, is never created nor destroyed. It can be converted from one form to another, but the total energy remains constant. Okay? Always. We may not see where that energy goes, but it goes somewhere. Okay? Now, we are constantly being hit by radiant energy from the sun. We're also radiantly emitting energy back into space. The part that gives us a little bit of problem is the fact that with more greenhouse gases, more of the energy is trapped on Earth, and then we get the global warming. This author is not super big on that, but it is an issue that we are facing today. In fact, many ways today in today's election, because there's really a lot of science is on the line here. Okay, don't want to get political too much, but it's important. Okay, so now we move into 13.4, energy sources today. Now, there are some things here, myths, mistakes, and misunderstanding. Is it a myth that leaving your computer on all the time uses less energy and makes it last longer? Probably not, okay? I think back in the old days when you were having to heat up vacuum tubes and things like this, yeah, there could have been some extra loss there. But today's computers don't have vacuum tubes. They have things like transistors and stuff. Probably the longer you have it on, the more heat you're losing. Okay, it's just that simple. Okay, but I can remember back when they used to say with fluorescent lights it was cheaper to leave them on than to turn them on and off all the time. My younger brother was an electrical engineer. I think he still believes that. But I think they've improved the fluorescent lights so much that that's not a big concern anymore. LEDs are even more efficient than fluorescents. Of course, fluorescents were way more efficient than incandescent. Okay, so there are all kinds of scales there you can look at. So let's look at energy sources today. Now, the biggest source, now this probably is a little bit older than the one that's in your book. In your book, that shows petroleum as being 36%. Back when the slide was made, it was 40%. Pretty close, but that was even more. Petroleum. Now, where do we get petroleum? Okay. Petroleum came from, remember I said the energy coming from the sun millennia ago, long time ago. That was being trapped by trees from a long time ago, or other plant life. And then it was, we're going to talk about this in more detail, but that is long time storage of stored chemical energy. Okay. Petroleum was 40%, probably 10 years ago, probably down to about 36% now, but still that's the biggest sector we have. Probably 20 years ago, coal was number 2. That's still a hydrocarbon. It's a fossil fuel. It was at 21%. Today it's probably, well, when the book was written, it was down to 18%. Probably today it's even less. Okay? But that was number 3 before, because number 2 was natural gas. Coal was only 21, natural gas was 23. This was when the slide was done. When the book was printed, natural gas had jumped up to 36. Okay, that would be, no, I'm sorry, I'm looking at the wrong one. Natural gas was up to 27. Okay, whereas when the book was done, it was 23. Probably today it's even gone higher. Okay, now I don't know if it's matched petroleum yet, but it's getting closer all the time. In fact, the US, back when this was written, most of that petroleum was coming from overseas. Now, with more natural gas, we're producing more of our own natural gas, and we're relying less and less on petroleum. So we're about energy neutral here. But guess what? All 3 of these big ones here, 40%, 23%, and 21%, that's 83% on this diagram was fossil fuels. Okay, if you look in the one in the book, that's 18, 36, and 27. That's 63 and 18. 63 and 18. Goodness, I'm not doing math well at all today. Okay. 18, 27, and 36. I can't read. Okay. 18 plus 27 plus 36, if I can read. That was a total of 50% of, that's wrong. 18 plus 27 plus 36. 81%. 81% of the fuels we're consuming approximately today, fossil fuels. Let's see what they were in the past. 40 plus 44, that was 84%. So it's not changed that much. The percentages have shifted around some, but it's just not that much less. 81 versus 84%. We have dropped a little bit. Agreed. Absolutely. Good. Moving in the right direction, but moving very, very slowly in the right direction. Okay? Let me plug my phone back in so it'll be ready for lab today. Okay? Now, where have we picked up that little bit of slack we had? Well, The figure in the book classifies differently. Okay, nuclear in the book was 8%, nuclear on the slides were 8%. Not that much has changed, a little bit has, but you see we're using more too, so even though we've got more nuclear power plants, the percentages are about the same. Okay, now what the book does is combine everything else together. Other meaning geothermal and solar, hydroelectric, biomass. Those added together are 3.5 and 3 would be 6.5, another 0.5 would be 7%. In the book, the renewables are 9%. Okay, so yeah, we picked up just a tad, but not very much. And it's still such a small piece of the pie. We are so dependent on these fossil fuels. Okay, so the energy sources today, it says primarily wood. There's not that much more wood being used, but it is used, to coal, to petroleum, with increasing industrialization. So what they mean here is not too distant into the past. It seems like a long time. We were wood, okay, was our primary source. We cut trees, we heated our houses, we ran our old locomotives on wood. We did just about everything on a wood economy, you might say. Then people learned about coal, they mined coal, they got better at it, and with increasing industrialization, it was maybe a little bit cleaner than wood, because wood produces an awful lot of ash, but coal produces an awful lot of smoke, okay, and ash, okay. Then they moved to petroleum. Petroleum, much cleaner than coal, much cleaner than wood, but in today's environment, the natural gas is even cleaner than petroleum. There's not as much wastage, but they're all fossil fuels. They all will run out in time. We need to be focusing on that. So 89% can be traced to photosynthesis. Some of that photosynthesis was a long time ago, millennia ago. The petroleum, the coal, and the natural gas were a long time ago. The biomass, another 3% there. So that is where they got their 40 and 43, 44 would be 84, plus 3% is 87. They said 89. A little bit of this other probably came from that as well. 89% to photosynthesis. Biomass is recent photosynthesis. The others are ancient photosynthesis. Now, what do we use these energy sources for? About a third of it is burned for heating. Heating houses, heating industrial purposes or whatever. 2/3 are burned in engines and generators. Generators producing electricity, which may later be used for heat, but also burn in engines like car engines, boat engines, airplane engines, all sorts of engines. That's where about 2/3 of our usage for those energy sources go there. So guess what? We are fossil fuel hogs. 84%, 83%, whatever, we're hogs. We just are going to have a hard time weaning ourselves off fossil fuels. Okay, so let's look at those fossil fuels. Petroleum. Now, you probably have seen the old movies and stuff like this. Someone's out there drilling for oil, and all of a sudden this gusher comes flowing into the air, and they start capturing it and doing that. That's, yeah, some oil comes from there, but most of the oil is from oil-bearing rock. It's not necessarily just liquid. There is some of it out there. We've already harvested most of that, easy to get to oil. Okay, it's from oil-bearing rock that they have to pump and pressurize and force it out of the rock. Okay, now where did it come from? Organic sediments. What do we mean by organic? things that were one-time living organisms, as in trees, plants, grasses, even animal byproducts. These sediments transformed over time, and time is a huge factor there, as in thousands, multiple thousands of years. Okay? Now, also assisting in the process were bacteria, pressure, and temperature. Okay, now the bacteria were the things that broke down that original organic material. Okay, the bacteria, mostly what they call anaerobic bacteria, bacteria that don't depend on oxygen. They break down these complex carbohydrates, these oils and things like this, and under enormous amounts of pressure, because they're deep, 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 deep into the crust of the earth, and at very high temperatures from being all that pressure and friction that you have, that creates a rise in temperature. This ultimately produces the oils. Okay. Now, natural gas formation is similar, except generally at even higher temperatures. Okay, a lot of the sort of the nasty product that are in petroleum, a lot of them have been kind of filtered out by the natural gas process. But petroleum and natural gas are often found together. What made that oil spew into the air was all that high pressure natural gas that was in there as well. Okay, now supplies are limited. Okay, way back we were finding lots of petroleum products. Oh, here comes Dre. Let me get Dre in here and let me get him marked here. Okay, Dre is here now. Bottom part of the alphabet is trying to catch up with the middle part. The top part is still lagging pretty badly, except for a few people. Okay, now if you watch the old movies back, probably I'm guessing in the 20s, perhaps 30s, maybe teens, Texas was finding all sorts of oil supplies. Oklahoma, different states like that. Basically, they're vast majority of them have been used up. Okay, Alaska still has some potential. They've been mining petroleum there for quite a while. A lot of the ecology up there is very, very fragile. So to do a lot of petroleum exploration there could be messing up a lot of really delicate ecosystems. Okay, so what they've started doing was drilling in offshore wells. Gulf of Mexico, for instance, has quite a bit of both natural gas and petroleum underneath it. Some of these wells are as much as a mile deep. I didn't even know the Gulf of Mexico was that deep. But back when the Gulf oil spill happened, that was about 10, 12 years ago, boy, did we ever find out what the risks were then. Now, at the time this slide was done, more than 50% of our petroleum was being imported, mostly from Saudi Arabia, Nigeria, Venezuela, other countries like that. We were getting lots of our petroleum there. But like I said before, we've increased the natural gas production, decreased the dependency on imported oils, and now we're it's pretty close to 50-50. Not over 50% imported, a little bit less than 50% imported. But it still means we're getting an awful lot from overseas. We are energy hogs. We really, really are. But that's petroleum. Let's go to the next, which I can't do because the slideshow isn't doing, is coal. Now notice the similarities between coal and petroleum. Some differences, some similarities. Accumulated plant materials. That's the same place that we were getting petroleum. Organic sediments transformed over time by bacteria, pressure, and temperature. This accumulated plant materials processed over time by pressure and temperature. Now they left off the bacteria, still involved with it, The progression here was basically the swampy type areas produce what they call peat. Peat is very high concentration carbon materials from accumulated plant materials over hundreds or thousands of years. That over time, pressure, bacteria, goes to a substance they call lignite, which is a coarse form of coal, okay? Not very clean, but it's coal. That goes to subbituminous coal, and one of those is called anthracitic coals, and then ultimately to bituminous coal. Now, bituminous coal is much cleaner than peat, lignite, or subbituminous or anthracitic coal, but it's still pretty dirty, okay? So this hasn't been transformed as completely as petroleum has, and certainly not as natural gas has. So it has a lot of trash in it. Impurities abound. You have some minerals that are in there, and that leads to ash. Just for an example, now we were just dealing with wood. When we were burning the trash over the weekend, the wood product, the pecan limbs, pecans, because they're nut trees, have a fair amount of oil in the wood, so they burn really hot. And we were burning in a chimenea, they call it, and at the end of the day, it was just a fine coating of ash in there, but there was plenty of ash. Now, some of that did escape. There was some that did become soot in the chimenea, but most of it burned away pretty good. But the minerals that were there led to ash. Okay, same thing happens with coal, same thing happens with petroleum, same thing happens with natural gas. There are always impurities, but the more processed it is, wood to coal, wood to peat, to lignite, to different forms of coal, later to petroleum, later to natural gas, the more of that process that happens, the less ash you have. Also, the less sulfur you have. That wood, I'm sure, probably had a fair amount of sulfur in it. Coal has quite a bit of sulfur in it. Petroleum has quite a bit. Less than coal, but still quite a bit of sulfur. Natural gas has the least amount of sulfur. So that's why it's a cleaner burn than even petroleum. Okay? But when you burn sulfur, you get sulfur dioxide. Sulfur dioxide, when you combine it with water, gives you H2SO3, which is sulfuric acid. That is mean stuff. You don't want that to be hitting your clothes, hitting just about anything. It really is pretty mean. And yet we burn coal like crazy. We burn even natural gas and petroleum products. We always produce excess sulfur byproduct, which are pollutants, really bad pollutants. Now, all three of those, petroleum, natural gas, and coal, that is what we call our fossil fuels. That means that that energy that was absorbed from the sun millennia ago, thousands of years ago, that has been stored as stored chemical energy for thousands upon thousands of years, and now we're burning it up as fast as we can put our little grubby paws on it. That's not sustainable. And yet we just do more and more and more. The fossil fuels, believe it or not, they're going to run out. Period. Okay. They're going to be messy as they run out with all this pollutant. They are there. The ash, all that pollutant is there. We've done a much better job of cleaning up our production, but we still are polluting like crazy. Okay. And a lot of that carbon dioxide that's given up, which you thought was pretty clean, that now is a greenhouse gas, and that's contributing to global warming. So we're losing all the way around. Okay, so let's go on to next, moving water. Now that's renewable energy, because for those of you who are in, oh, here comes Valerie. Good deal. Valerie got here today. Okay, Now the bottom part of the alphabet is really coming in strongly. Bottom three are here. We missed one. Next four above that are here, and then we have big gaps before we get to the two near the top of the alphabet. So keep them coming, folks. Okay. Now, for those of you who are in Physical Science 111, you'll know that the evaporative effect, again, where is that coming from? Heat from the sun. That is evaporating water off the oceans. The water vapor goes up into the air, gets picked up by the winds, okay, and over time falls back to ground, sometime over the ocean. That's not helping us much, but over land, the gravitational potential energy as that water vapor moved up, moved over land, and falls down. Then it hits the streams, the creeks, the rivers, and whatever. And what they do then is build the dams on those rivers, streams, creeks, or whatever, and then use the falling water in the dams to convert to electrical energy. But all that energy came from the sun. The vast majority came from the sun. It's renewable energy because rainfall is always happening, but that's where you get the electrical energy, the fall of the rain. These hydroelectric plants only generate about 3% of U.S. total energy consumption. And we are probably, in the world, probably produce about as much hydroelectric energy as anybody does, and it's only 3%. Remember the diagram back there? I can't show it to you now. The thing won't go backwards. Here we go. Oops, there it was. Hydroelectric, 3.5% they showed here. In the book, it was all combined under renewables at 9%. Okay. It's great using moving water. The problem is the growth potential is limited by decreasing availability of new sites. Okay, you might say, well, wait, we have lots of rivers, don't we? Yes, but the rivers where you have the greatest fall, that's what you depend on, that potential energy of the water. For the greatest fall, you have to be way upstream, okay? We've already dammed up most of that water, okay? If you think about northern Alabama, Lay Lake, Gunnersville Lake, Smith Lake, there's one outside Tuscaloosa, is that Lurleen Wallace or something? All these have all been dammed up, okay? They did it back when land was cheap, and they could buy out the land from the people who were going to be, the water behind the dams was going to flood. They bought those out when they could, okay? Now, most of the rivers are in flat areas. If you were to try to dam up some of these rivers south of here, you would cover huge areas of land, very productive farmland, cities, towns, you know. Nobody wants that to happen. So most of the growth potential is limited by decreasing availability of new sites to build the dams. There may still be a few, but dams are pretty expensive to build. They're very expensive to buy the land. There's just a lot of economic things moving against you here. So moving water, we're stuck at 3% or less, okay, for probably from now on. Too bad. It's very clean energy. Okay. Nuclear energy. Now, the nuclear energy on the sun is fusion of hydrogen to helium, and then later maybe fusion of helium to carbon, and later maybe fusion of carbon to iron. Those fusion processes take place in bigger and bigger and bigger stars. For those of you who have had Physical Science 111, that's all coming from nuclear fusion. That's what's happening out there in space. What we're doing, nuclear fission, that's taking great big molecules. The others, hydrogen is the smallest molecule you have, atom that you have. Helium's the next smallest. Carbon's not much bigger than those. And then you own up to iron or so. That's nuclear fusion. Nuclear fission starts with the big, heavy, unstable isotopes like uranium and plutonium, and by bombarding them with a certain number of neutrons and things like this, you create nuclear fission, which you blow up and separate the big molecules, big atoms, into smaller atoms. But when you do that, you create a whole bunch of really nasty radioactive material that lives for a very, very long time. Now, a lot of energy is given off by nuclear fission. Not as much as fusion, but a lot of energy is given off. That energy is used to heat water in a reactor to very, very, very high temperature steam. That high temperature steam is then used to turn turbines that produces steam, turn to generating turbines, and that's where you produce your electrical energy. Now, for those of you who are familiar with naval vessels, as in aircraft carriers, heavy cruisers, submarines, many of those actually use nuclear reaction to produce the steam that propels the ships, whatever ship it is, forward. Now, they also generate electricity as well. That gives you electricity on the ships. And it's all well and good. They are very good at it. They've been doing it for decades, and they've got it down to a fine art. The electrical power generation, they thought they were pretty good at it until two major things happened within just a few years of each other. In the Soviet Union, they had a really major nuclear disaster called Chernobyl. Okay? Chernobyl, I don't know exactly why or how or anything else, but the nuclear power plant basically went out of control and melted down. And they created so much nuclear radiation illness, that people were affected for miles and miles and miles around. Not only were they affected for miles and miles and miles around, they were affected for years and years and years, because that radiation does not leave the environment. Okay? I'll just give you an example, and this really is an example. Chernobyl is in the part of what was the Soviet Union that now is Ukraine. It's a separate country now, but it was part of the Soviet Union. That was one of the big Union Soviet republics, so it was probably number 2 behind Russia, but Russia was so big everybody called it Russia, but Ukraine was number 2, but way distant number 2. And they had Chernobyl there, and it seems like something on the order of 20 years after Chernobyl, that disaster happened there. There's still so much radiation there that has not been contained. People living anywhere close to it are still being affected by it. There were children born after that disaster with all kinds of problems. Physical problems, mental problems, cognitive problems, all kinds of problems. Okay? There were agencies here in the U.S. that would pay to have children brought over out of that environment so they could live at least one summer under normal conditions and maybe grow a little bit stronger and better and more resistant to the ill effects that they were suffering over there. Birmingham, there were several churches in Birmingham, or a collection of churches, that actually sponsored children to come over for 3 months this summer, just to come over and have a cleaner environment in which to live. And that helped them big time. There was a couple from here in Birmingham, I can't remember which one. One of the members of the couple was actually from South Africa, I think. I believe it was the woman, but it may have been the man. I don't remember which. But one was a pastor, and they actually adopted a boy. from a orphanage over there. It wasn't that his parents had died, but when he was born and he had defects, they just left him on the stairs outside of the orphanage and left him. Okay, and the orphanage took him in, and he was being raised in an orphanage. An incredible kid. Okay, I got to know him. He came and took classes, math classes at, let's see, were we Bessemer State Tech or Lawson then? I probably were just shortly after we became Lawson. One of his problems was he was missing a right arm. I mean, there was nothing there. He was born without a right arm. I think I heard sometime that he had one finger coming out of his shoulder. That was it. The nuclear radiation was so damaging to his DNA, it completely messed him up. He had a hair lip that could be repaired. He had some cognitive loss. Who knows whether that was caused by the radiation or caused from the orphanage, I don't know. But he was just a delightful young boy. And this couple raised him, adopted him. And he was trying to become a physical therapy technician because he wanted to let other kids who had problems, not maybe as severely as he had, but had problems, to learn to live with that. And he had trouble with his math, but his mom helped him a lot. He took my math classes, and I helped him as much as I could, but I recorded all the lectures so his parents could help him at home. He managed to get through his 2 math classes, and but still I don't think he could find a job, because who wanted a one-armed physical therapy technician? They wanted someone with 2 arms, you know. So I don't know what's happened to him, but he's was a delightful child, delightful young man. I'm sure he's working hard at something, because he just wouldn't sit still, I don't think. But anyway, the safety to nuclear power generation is controversial. Now, here in the U.S., we had an incident at 3 Mile Island. Now, that was a much safer plant than Chernobyl had been. The Soviets cut corners like crazy, but we still had a problem there. We had a nuclear meltdown. We had more safety in place, but still had the meltdown occur. Somewhere up in New York, Pennsylvania, some area up there. It was on an island. They basically isolated it, okay? But it wasn't good, okay? More recently from then, there was a major earthquake, marine earthquake off the coast of Japan that created such a big tidal wave, it flooded the nuclear power plant at Fukushima. And that's been during your lifetime. You probably heard of that one. And it was probably as severe as Chernobyl, had potential for that, except that the Japanese have built super good safety precautions, but still had so much nuclear waste. They don't know what it's going to do to the Pacific Ocean there. They don't know how long the effects will be felt. Now, even when there's not these major disasters, every submarine, every battleship, aircraft carrier, every cruiser, every nuclear power plant that's in existence is producing waste product, okay? And that waste product is highly radioactive and will stay radioactive for thousands of years. Thousands of years. What do they do with it? Right now, the practice is to store it in the very safest containers they can possibly put together and bury it as far underground as they can possibly bury it, and hope that it doesn't leak out before it's lost most of its the toxicity. We don't know. We don't know how long those stainless steel containers will keep the nuclear waste there. We don't know. We don't know how long before something leaks into the groundwater, before maybe a critical mass happens and things start heating up down there. Who knows? Nobody knows. Even in the safest environments, the waste product, what do you do with that? Very controversial. Shortly after we moved to Birmingham, I was working, I think probably at UAB or at Southern Research Institute at the time. This is just unbelievable. Y'all know where Greene County is. That's south and west of here, basically going down I-59, I believe it is. And they have huge landfills down there. A lot of the cities, like I think probably Birmingham and Tuscaloosa and other areas, ship their trash and garbage and things to huge landfills in that very, very poor county. And that's how they maintain part of their existence down there. Well, nuclear power plants from the Northeast had all this extra nuclear waste that they were having trouble getting rid of. They finagled the way around some issues and were shipping some of that to be buried in Greene County, Alabama. Fortunately, someone found out about it, stopped it in its tracks. It may have gotten as far as Birmingham. They turned it around and shipped it back because that was not something we wanted happening in our backyard. But they thought they could get away with it because Greene County was such a poor area. They thought they would take it if they paid them enough. So lots of controversy. What do we do with the waste product? Okay, let's move on to energy sources tomorrow. We need to come up with something, folks. Fossil fuels, yeah, we've got enough to last us a while, but they're harder and harder to get to. By the way, a lot of coal is mined in Alabama, but that's some of the dirty coal. We ship it to South America or places like that. They use the dirty coal. Guess what? It still gets into the same atmosphere that we breathe, okay? It's just a little bit further away. We then bring in coal from out west, Wyoming and some of those areas, which is much cleaner coal, but it's still awfully dirty, okay? So we're just robbing Peter to pay Paul in messing around with fossil fuels. They can't last that long. And it's fossil fuels that were deposited in our earth millennia ago, thousands upon thousands of years ago. We're using them as fast as we can get them out. We've got to have alternate sources, both for the cleanliness of it and also the fact it's going to be harder to get. So what are some of the alternative sources of energy different from those used commonly today? Okay, today it's fossil fuels, coal, petroleum, and natural gas in whatever order. Okay, it's probably now petroleum, natural gas, and coal. Maybe in the future it'll be natural gas, petroleum, and coal. But guess what? It's there. That's what we got. We're also using a good amount of nuclear energy and falling water. Falling water is almost fixed at 3% or less. Nuclear energy, finally they've started doing a bit more of it. They probably have improved the technology of it, but they still have all the problems with it. There are plenty of problems with coal, petroleum, and natural gas. Natural gas has fewer, petroleum fewer than coal, but coal still has, it's dirty. It's just plain dirty. So what are we going to do tomorrow? Well, we hope to be using more and more and more solar. Solar cells, direct solar energy, we have traveled a little bit in Europe, and you'll go by these whole communities that every roof, or most of the roofs of all their garages, their houses, their buildings, whatever, they'll have solar cells on top. So they are producing more and more electricity with solar. Well, of course, one problem is the sun's only out on average half a day, 12 hours. This time of year, it's less than 12 hours. That's when we need more solar energy, but we have less of it. In the summertime, yeah, we can use it for air conditioning, but there's more of it then. but there are problems with solar. But it's clean, it's renewable, and it's here. But it's only here about half the time. Geothermal energy, that's using the heat from the earth. And we talked about this in Physical Science 111. Iceland, for instance, that's a cold country, a very cold country, okay? That's why they named it Iceland. But guess what? They probably pay smaller energy heating bills than we do. Why? Because they're a volcanic island. And that volcanic island, they have learned to pump water down onto the hot rock that's underneath there, pump it down in there, and generate steam through the hot rock, which is totally renewable. Okay, that's always there. Okay, so they have done a good job of that. Hawaii, I think, is doing a fair job of that. Other places. Hydrogen gas has a lot of potential, but it has a lot of problems as well. Okay, hydrogen burns like crazy. It will burn almost explosive in its burn, so you have to really control it carefully. But guess what the byproduct of hydrogen burning is? Hydrogen plus oxygen, H2O. Water is the byproduct. No sulfur, no bad gases, nothing else. It's a very clean burn. Very clean burn. But in order to get hydrogen, you have to put so much energy in, because hydrogen reacts with just about everything. So you wind up spending a lot of energy to produce hydrogen gas, so then you can turn around and burn it, and you don't get that much net energy out of it. Now, fusion, I mentioned on the sun, that's what's happening with fusion. They're trying to do this on small scale. They call it cold fusion, some people do, much lower level, but if we can manage a way to control the fusion at relatively low temperatures, there's a vast amount of energy there. However, getting it out, the technology just isn't quite there yet. Now, one thing they didn't mention here, and it's sort of surprising, wind energy. Now, maybe they were including that under solar, because some of the wind energy does come from the sun, but not all of it. Geothermal, no, that's not thermal. Wind energy, we're doing a much, much, much better job of harnessing wind energy. But of course, some areas, like I look out my window right now, there's hardly any movement of the leaves at all. We would not be able to produce a lot of wind energy today. Now, a few days ago, when the hurricane came flying through, yep, for that day we could have produced quite a bit of energy. But then the windmills would have been sitting idle for weeks after that. Okay, so there's problems. There's some areas that the wind blows almost constantly. San Francisco, Chicago, some of those areas, they put up the wind turbines and they keep them running just about 24/7. So there's a lot of potential there for wind energy. Totally renewable. Now, some people gripe and complain that birds fly into the turbines and stuff like that, but birds are flying into pollutants all the time, so I don't think it's any worse than others, but some people will complain about anything. All right, so let's look at some of the solar technologies. We mentioned solar. One is solar cells, like I was describing before. In fact, some of you who have calculators, I bet you they're almost totally powered by solar cells. If you have that little bank of windows up there on top of your calculator, it's using light to convert light into electricity. Those are solar cells. Those things that you see, the panels that you see on top of buildings and stuff like that, those are solar cells. In Birmingham, I don't know if you've noticed it before, downtown Birmingham, they have these bike racks that people can rent bikes. I think they're usually green. I can't remember what the name of the company is, but you can do that. Those are all under little structures, and on top of the structures, they're solar cells, because some of those bikes actually are battery assisted. Because Birmingham is pretty hilly, and some people need a little help getting up and down the hills, or up the hills anyway. So those are they're not pulling power off the grid, they're pulling power directly from the sun. So solar cells, yeah, there's potential there. How big a potential? Not too sure, but there is potential. We need to use all that we can. If you've ever noticed these places where they have the high voltage power lines that go through, the power companies cut down the trees all around those, and you have these things. If you drive down the interstate, you'll see them sometimes. Why in the world does every one of those big tower things have solar cells on them that are feeding into the grid? Well, because the power companies, their business plan is to convert from petroleum, natural gas, coal, or something else. They don't want to be into their competitors' solar cells. Okay, it's a pretty sad situation. Power towers, mirrors focusing sunlight to heat water for steam generation, which then is used. I went to Georgia Tech as an undergraduate and then went back for a couple terms of grad school there. And in the time between my undergraduate and grad school, they had built a long power tower, only it was horizontal, not vertical, and they were using that for steam generation, using a mirror to focus light energy onto a pipe which produced steam. There are other things like passive applications designed to use solar energy flow naturally. One of my father's first cousins married an architect who had graduated from Duke University, and he was older than my dad, and my dad would have been 99 years old this year, so actually it already would have turned 99. He would have been 100 years old next year, in 21. And Bob Connor was probably 5, 10, 15 years, maybe not 15 years older than my father. Oh, here comes Rucker. Good deal. Rucker's here. All right, the top part of the alphabet gets a little bit of a boost there. So Rucker's here. That should give us 3, 7, 8, 9, 10 students. We finally broke double digits. Let's see if we have. Yep, 10 students. And hopefully I've got them all in. Yep, don't see anybody still waiting out there. Okay. But anyway, Bob Connor was an architect, and he designed homes and businesses and things like this to, as much as possible, face to the south, and face at an angle such as very close to the latitude. That was the angle of his roofs lines, so that in the summertime it shaded because the sun was above that and kept the building from getting hot, but in the wintertime the sunlight came in and had lots of windows on that side, and therefore it heated the building in the wintertime and in the shade of the building in the summertime with a big long eave over there. So he was doing some passive applications, I don't know, 60, 70 years ago. So people have been designing solar energy concepts into buildings for a while. It wasn't a very popular thing because energy was rather cheap, but he saw it coming that you needed to be conserving. Then there's more active applications, for instance, solar collectors used to heat water, air, or some other liquid. That would be like power towers. One thing that we really should be doing, and we don't, I wish we did it, but we don't, is have water pipes on the south side of our roofs, okay? And if you did that, you would be heating water all the time that the sun's shining. That's even in the wintertime. If you coated the pipes properly, you could have heated water, and guess what? That heated water can be used for your hot water heaters, okay? So rather than burning natural gas or heating with electricity, you would use using an active application of solar energy to heat water. That's just about the most efficient way you can use the sunlight energy, is to heat water, okay? And that's used for heating or electric generation, okay? Those are solar technologies. more wind energy. They finally mention it here. That's not really that much of a solar technology. It is some, but the turbines generate electricity, but in some areas the wind is inconsistent. So like I said today, no wind out there, no generation at all. Okay, other days, pretty decent amount of winds, but it's just inconsistent. Now, why I object to saying that's a solar technology, the wind, much of the wind production of the earth is from the spin of the earth, not from solar technology, the actual spin of the earth. Now, another is biomass. Now, in a long time ago, wood was biomass, okay? And people burned wood, Well, that's sort of dirty, okay? Not wanting to do that much anymore, but that's plant material formed from photosynthesis, burned directly or converted to other fuels. And what they've started doing now is studying things like some of the rapidly growing grasses, and if they can convert those to a form of energy like maybe natural gas, which can be done, then you can burn that directly. And they do have technologies to keep the dirtiness out, the ash out, and really be pretty efficient with that. Now, I'm going to also bring up another biomass here that they don't mention directly. But if you can imagine, I don't know if any of you have ever worked at a fast food place, especially a hamburger joint. Some of you probably have. And you probably know that lots and lots and lots of grease and oil is left over, right? And you have to get rid of it. Well, what they're doing now is trying to reprocess those oils, vegetable oil, possibly even animal fats and oils, take that, reprocess it, and use that as a fuel source. That gets rid of a waste product, but uses it again and again and again. That's biomass. The more we do of that, the better we can do. When I was at University of Georgia in grad school, Georgia was a fairly spread out campus, and they ran buses all over campus. That was part of your tuition, not tuition, but fees that you paid for the buses. And because if you lived on one side of campus, had a class on the other side, you had a long haul to do. The buses got you there quicker. Well, Georgia is a big peanut producing state. They ran some of their buses on peanut oil rather than petroleum product. Okay, biomass. Brazil doesn't have much petroleum product, so they were having to import most of their stuff. Oils and stuff. They started producing more and more soybeans to take the soybean oil, which is a very good oil supplier, and make their fuels from that. The trouble is they burned down rainforests to grow more soybeans, so they were sort of counterproductive there. Okay. Agricultural and industrial heating, direct use of sunlight to dry grain, cure paint, and stuff like that. Of course, that was done in the past. Now we're moving back to that to take more advantage of solar technology. Now, here's one that's not necessarily solar technology, but is a little bit. Ocean thermal energy. Uses the temperature difference between the waters at the top of the ocean, which are usually pretty warm, and deep in the ocean, which are not that warm, but because of that temperature gradient you have there, using that to generate electricity. Now, to me, that seems like quite a stretch. To me, something that would be far more reasonable, in some areas, you have these tidal surges that come in and go out twice a day. Well, put your turbines on that river and let it turn the turbine one way going in, another coming out, and do that twice a day. Seems like to me you could generate quite a bit of electricity there just based on the tides. No, not even necessarily a solar technology, except for the fact that the sun is, the gravitational effect of the sun and the moon are contributing to those tides. So it seems like there's lots of possibilities there, but all these are minuscule compared to our use of fossil fuels. We've got to do better. Geothermal energy, the next one we mentioned there, that was from hot, dry rock, and that's about 85% of the total resources that is associated with volcanic activity. Fortunately, we don't have that much volcanic activity in the U.S., but there's some, mostly out west. Okay, Yellowstone has lots of volcanic geothermal energy there. Okay, Mount Shasta, Mount Rainier, a lot of those mountains out in the west coast of the U.S., high volcanic potential there. They're not volcanically active now, but they have been in the past. Can we drill down into those mountains and hit the hot rock again and use that to produce steam like they do in Iceland? And like I said, Hawaii is all volcanic material there underneath those islands, so they are using quite a bit there. Now, there's geopressurized resources, underground reservoirs of hot water containing natural gas. So there you can extract the natural gas from the water, but also use the heat of the water that's there. That's 14% of the geothermal energy. 85% are from hot, dry rock, 14% from the geopressurized. That gets you up to 99%. Most of that is dry steam, very rare, only 3 sites in the U.S., so it's not a huge source, but man, we need to use every bit of it. Hot water makes up most of the recoverable geothermal resources. What they do in Iceland, they pump that hot water underneath the roads, underneath people's homes, and their floors are built with pipes installed so that that hot water keeps their houses heated. In the very, very, very cold winter, they have almost zero energy bills for heating homes and businesses. Okay, so that hot water can be circulated directly into homes, businesses, farms, and other places like that. Okay, there's lots of potential. We're barely scratching the surface, but we need to be doing it more and more, faster and faster. And yet, politicians tend not to want to change. They get their big bucks from existing companies, not from new resources. Not good. Now, we mentioned hydrogen. Oh, here comes Brianna. I think she was here before and must be coming back. Yeah, I already had Brianna here. Okay. Now, hydrogen is an energy source. The problem is with hydrogen, it's the lightest, smallest molecule that there exists. So therefore, it's the hardest thing to contain. It'll go through rubber, it'll go through pipe, it'll go through just about anything because it's so light. And it's so light, it takes a lot of it to do much, so they usually pressurize it. Okay? Well, when you pressurize a very light gas, it's very easy to have leaks. And because hydrogen is extremely explosive, you don't want a lot of hydrogen leaks because one of them could explode. Have any of you ever heard the term Hindenburg? That was an early blimp. Yes. What's that? Yes. It was I think in Germany, it sounds German anyway, and that they made the early blimps out of hydrogen because it was the lightest gas, but they had something to happen. Some people thought it might have been a lightning strike. Others thought they may have hit something and just a little bit of friction. When hydrogen burns in the presence of oxygen, it's explosive, and it did explode. I mean, a fireball like you've never seen before. Okay? However, guess what the byproduct of that burning of hydrogen? Water. Okay, so it's a clean source, a very clean source, but the storage, you have to chill it to very low temperatures. That takes energy to do that. There's just all sorts of problems with it. It's a clean energy source. Now, where do we get it? You could get it from water, but it takes just as much water energy to separate hydrogen out of water as you get to burn energy hydrogen to to produce an energy source from the hydrogen. So it sort of washes out. Okay. The possible problems: best used as liquid hydrogen, which is incredibly cold, which means you have to refrigerate it like crazy. There goes all your energy benefit trying to keep it cold. It's extremely flammable and extremely leakable. Okay, and those are bad combinations to have. Okay, they are working on what they call fuel cells, which convert the hydrogen through a chemical process and then use it almost immediately, so you don't have the storage problem and you don't have the pressure problems. There are potentials there. It's tough though. There's a lot of technology that has to be developed to use it. And I think we're getting close to the end. Yep, we are at the end of the slideshow. Now let me hit just a few things that I haven't mentioned. Grow your own fuel, science and society. Have anyone ever heard of biodiesel? That's what I was talking about. They did actually at University of Georgia, using peanut oil, and Brazil using soybean oil. In some places they use corn oil. The problem is that when you start using food sources like peanuts, soybeans, and corn as your energy source, that drives up the price of your foods. And when you drive up the price of the food, then people starve. Okay, so that can be a problem. However, the idea of using old oils, as in burn engine oil, oils that you use to fry fish, fries or whatever, using that, that has a lot of potential. There's a lot of cleanup you have to do with it. The person behind the science, they mentioned this in this chapter, is James Prescott Joule. The unit Joule is named after him. Nice blurb on page 78. A great potential idea for a paper topic, but this cannot be the source of your paper topic. You have to get the source from outside. You'll see several other people mentioned here. A guy named William Thompson, whose title was Lord Kelvin. He took sort of Joule under his wing and really helped him, and they had a good long-lasting relationship as far as producing great science. Okay, so there's plenty there you can look at. Concepts applied, they talk about city power. You can look at that if you'd like. Conserving energy. They also miss mistakes and misunderstanding. They talk about recycle or reusing. That is reusing, not recycling. Now, one place that they do use plastic bags, and my wife and I put together 2 chairs. She did most of the work because I was doing other things, but we have bought these chairs that are made out of polywood, basically recycled plastic bags, pressed together, and it will take screws and things like this, and you can put them together, and basically they're heavy, but you don't have to paint them, you don't have to do anything. They last a very, very, very long time. That's a recycling of things. And that pretty much wraps up the chapter. Nothing replaces reading the chapters. You'll hear me say that every chapter. There is a summary at the end of this one. This is on page 82. It's probably shorter than most of our summaries are. I don't know if I can get it all on one page there. There's the summary on page 82. There's the summary of equations. Fewer than last chapter, but still 5 pretty important ones. They can be rearranged in different orders. And then there's key terms, probably a few fewer than most chapters have. They're listed alphabetically, but they have the page number on which they're first defined or described. Applying the concepts, this will be most similar to what your test questions are. Not the same, but similar. Most of your test questions will be multiple choice like this. They have here 36, which is fewer than most chapters are, but they give the answers. Your test is probably going to be 20 or less, but it's not going to be the same question. But if you know the concepts here, you will do well on the test. Questions for thought, there's 12 of those, which is a few fewer than normal. But for further analysis, there's 9 of them. And I can't think of another chapter in the book that has that many for further analysis. So it has a few more of those than normal. Of course, the answers aren't given except you have to find them in the text. The parallel exercises, if you do have the big thick book, the Group A exercises have the answers in the back. Group B do not. Okay. Those are the things to study for your test. I will try to, after class today, if there's time, if the lab ends a little early, I'll try to post the test for Chapter 3. I think I have it ready. I don't think I posted it yet, but I will be posting it later. I may have, like I said, I can't remember. I'm teaching so many classes, I don't remember which ones I've done and not done. How are we doing on time? 5:03. We got about 45 minutes, 42 minutes before we are ready for lab. Any questions on Chapter 3? Okay, if not, let's move on to Chapter 4. So I'm going to get rid of Chapter 3 there and see if Chapter 4 is up here. It was up here, now it's not. Okay, let me see if I can find it anywhere again. So what I'm going to have to do, and this aggravates me, I get it set up before class and then it throws it away. Okay, so there's Chapter 4, but now I have to get it so I can pull it up. There we are. Now, I don't know why Chapter 4 is different from all the other chapters in the entire book that I've taught. It uses a brown background and white type, or red or some other kind of type. You can see that here. All the other chapters are white background with black type or other color type. But Chapter 4 is a little different. I don't know why. But let's start from the current slide. And Chapter 4, is heat and temperature. Now, I don't know what you think about this. If you think those are synonymous words, they are not. Heat, and we're going to learn several definitions of heat, but basically it's a form of energy transfer, to be more precise. Temperature is a measure of how hot or cold something is. Now, certainly they're related, but they're not the same. Okay, they are related but are not the same. Here's the core concept, also on page 87 if you have the big book, or this would be 4-1 if you have the smaller book. A relationship exists between heat, temperature, and the motion and position of molecules. That's your core concept. We'll be talking about those relationships as we go. The relationship exists between heat, temperature, and the motion and position of molecules. Here's the overview for the chapter. Okay? One big kind of overriding term here is the term of thermodynamics. Now that prefix there, thermo, I'm sorry, I am so running out of energy. I think it's mostly the anemia, but whatever. I've got a sore throat too. Okay, thermo basically is the prefix that means heat. Thermo, thermometer, all those things have to do with heat. Dynamics means changing. Thermodynamics is the study of the macroscopic processes that involve heat, mechanical, and other forms of energy. Now, the last chapter was energy. We talked about mechanical energy, we talked about kinetic energy, we talked about potential energy. Now we're talking more about the macroscopic processes that directly or indirectly come about from heat and mechanical and other forms of energy. Now, the applications of this are systems with energy inputs and energy outputs. Now, for example, a heat engine, that car that you drove or whenever you've driven, that's a heat energy. You're taking in stored chemical energy, converting that to heat. That heat is then producing motion or other things that you need for your car. That's a heat engine. On the other hand, a heat pump. In our upstairs, where I am now, we have up in the attic a heat pump. What that does is takes mechanical energy. Now, this sounds bizarre, but it's a lot like a refrigerator, and that's mentioned right here too. And what it does is compresses the gas, and when it compresses the gas, that produces heat. When you use the heat from it, that's the heat pump. If you're blowing the heat away, that's where you get your refrigeration, because when you blow the heat away and then let the gases expand rapidly, that creates cooling. So heat pumps and refrigeration are basically two sides of the same coin. One's producing heat, one's producing cool. So it's rather bizarre. The same process that produces air conditioning will also produce your heat pump. However, in the downstairs, we're burning natural gas, and that's what produces the heat for the downstairs of the house. That was installed long before we moved here. We had them put in the heat pump upstairs. Now, all this thermodynamics all is based upon, but not concerned with the microscopic details. These are macroscopic, big scale things that you can see, measure, sense, those kind of things. They're based on, but not really concerned with what's happening on the microscopic scale. So the approach here for this chapter is discuss the underlying microscopic processes, relate the microscopic with the macroscopic, and then we'll turn around and study the laws of thermodynamics. So we're starting small, working into big, and then studying the big scale macroscopic processes. So that's basically how we're going to proceed with the chapter. So let's start with the small scale, molecular scale, down at the molecular level. All molecules are always moving. All molecules are always moving. No matter how cold they are, they're always moving. If they're moving, they have kinetic energy. All molecules are moving, so therefore they have kinetic energy. So this creates what they call the kinetic molecular theory. Now, what this is a collection of hypotheses, mostly pretty much understood to be true, but still not really certain on all of them, about the particulate nature of matter and the surrounding space of that matter. Okay? Now, we're going to hit this. We've probably already hit it some. We're hitting it again. We're going to hit it again in later chapters. The Greeks had the earliest written ideas on atoms. There was a Greek philosopher whose name was Democritus. Okay? He was a few generations before Aristotle and that crew. Okay? And he had this thought process. That's what the Greeks did. They thought about things. He said, what if you had a piece of iron? Okay? And you broke the iron into two pieces, and then broke that into two pieces, and then that. And you kept breaking down the smallest piece into smaller and 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 smaller. He said at some point you can't get any smaller. The smallest form of iron that you could get and still be iron, he called it an indivisible piece of iron. Well, the word in the Greek for indivisible was atom, or we get our word atom from that. That was the earliest written ideas on atoms. A thought process. Of course, he couldn't break things down into individual atoms. We still can't break things down into individual atoms necessarily, but that's the process. Well, then a few generations later, here came Aristotle, and he said, no, that's not true. Matter is a continuum. There's no smallest piece. It's just always a continuum. Well, people sort of shelved Democritus' idea because everybody believed Aristotle, even though he had it wrong and Democritus had it right. Okay, but let's move on from there. The current view is that matter is comprised of They say microscopic particles. I would say submicroscopic particles called atoms. Same thing he called them, the indivisible part that you can't break it down any smaller and still be that material. Those are the atoms. Atoms combine to form molecules. So here we're talking microscopic concepts here. Many of the macroscopic, the big level phenomena, can be traced to the microscopic activity on those levels. Okay, so this slide, especially the bottom half, is talking about microscopic. Atoms, molecules. Incredibly tiny phenomena. The macroscopic phenomena can be traced to the microscopic put together. Okay, now let's take that concept of molecules. Now, actually, before you get to molecules, let's go back to the atoms. If you have all the same kinds of atoms, a collection of all the same kinds of atoms, those form what we call chemical elements. Now, atoms are the microscopic process that build macroscopically your elements. They are defined by each unique type of atom. Now, I've already mentioned several of these. Hydrogen is the simplest atom we have, and it's a gas made up of only one proton, one electron. Okay, we won't go into that in this chapter. That'll come up in a later chapter. That's the simplest. Helium is number 2. Okay, it's 2 protons, 2 neutrons, and 2 electrons, of course. Okay, those are your atoms. They form unique chemical elements. That's the macroscopic process. Hydrogen, helium, lithium, boron, beryllium, go on and on and on. Carbon, oxygen, those are your elements, the chemical elements. You get up to iron, gold, nickel, chromium, those are all macroscopic elements made up of microscopic atoms, all unique types of atoms. Now, atoms then combine together to form molecules, like we saw in the last slide and the title of this slide. When 2 atoms combine to form a molecule, that's a brand new material, okay? And that new material may have nothing to do with what the atoms that formed it to begin with, okay? They formed it, but it has completely different processes. Now, compounds are the macroscopic idea from molecules. Molecules are microscopic, the compounds are macroscopic. Pure substances made up of 2 or more atoms chemically bonded together with brand new characteristics. Now, let me just give you a few examples. I think I've hit some of these before, but here's a few. Let's take hydrogen, okay? An explosive gas. We talked about that earlier, the Hindenburg, remember? Explosive gas. Oxygen is another element that is necessary for combustion to happen. So an explosive gas and a gas that is necessary for any kind of burning to happen, any kind of burning to occur. Well, when you combine those together, however you combine them together, that forms water, which we use to put out fires. Now, isn't that ironic? Explosive gas, another gas that's necessary for combustion to occur, but when they combine together chemically, you form a liquid that we use to put out fires. Okay, pretty amazing. Okay, water will not burn. Okay, hydrogen burns, oxygen is necessary for combustion, and yet the byproduct of those two chemically, because they're chemically bonded, they take on all new characteristics. I think I mentioned this one before too, if not in this class, in another class. Okay, sodium. Sodium is a very reactive atom, okay, element, okay. It's so reactive that if you are ever in a chemistry lab, sodium is going to be kept under oil. It's It's a metal per se, not a hard metal by any means. It's sort of, I think, a yellowish metal that's incredibly explosive. If you ever had it in presence of, okay, has my microphone gone off? Okay. Oh wait, now the internet, it just says my internet connection is unstable. That wasn't there before. Can you hear me better now? Yes or no? Okay, but you can hear me. Okay. Evidently the internet, my wife said this was going to happen. That with the election going on at some point of the day, and what is it now, 5:18, results are beginning to come in, especially on the East Coast, and I bet you everybody in the world is trying to get on the internet right now. Well, not everybody, but I mean a lot of people. So I wouldn't be at all surprised if our internet doesn't get pretty unstable. But can you hear me okay now? Okay, good. So let's take sodium, an explosive metal that if it's ever in the presence of water, it explodes. I mean, it's explosive metal. Okay? You would not want it touching your skin. It would burn you like crazy because your skin is mostly made of water. You would not want to eat it or drink it because it would. Okay. I have. Whoa! I just lost everything. Yeah. Evidently Zoom is falling apart too because I just lost Zoom. Okay, are you back now? Okay. Zoom just completely went off and came back on again. Okay, sorry about that. I don't know. What do you think? Are things going to get so unstable it's going to be like this the rest of the night? Do we need to? Okay. Okay, let's try it again. So let's go back to our screen share. Okay, yuck. Okay, wait just a minute. Let me see if I can get it back again. Okay, resume slideshow. Okay. It says, I think, internet connection is unstable. That's what it says. So I'm not going to talk. I'm going to keep talking, but not about physical science. Just waiting for it to get back. Am I any better or worse? Can you hear me at all? Okay. So let's go back. Sodium, an explosive gas. I mean, explosive metal. Okay. Chlorine, a green poisonous gas. Okay. Sometimes you'll see on the rail cars that go by, these tanker cars, and they will have something saying chlorine gas, stay away. If you ever had a derailment or something, they move people away because chlorine is a poisonous gas. So what happens if you take an explosive metal and combine it chemically with a poisonous gas? You know what you get? Salt that you use to put on your food. Unbelievable that two things so dissimilar, so dangerous on their own, would then make something that we use all the time, table salt. Okay, that's what chemical bonding does. It changes everything. Okay, so molecules are the result of those chemical bonding of different atoms. Molecule is the smallest unit retaining the properties of a compound. So compounds, okay, the microscopic concept for atom leads to chemical elements. The microscopic compound of concept of molecules goes into macroscopic compounds. So a molecule is the smallest unit retaining the properties of a compound. So here's the shorthand. Molecules can stand either for atoms if they're monotonic molecules, meaning only one atom in that molecule, or for bigger combinations of things, and can have multiple number of atoms, different kinds of atoms in a molecule. So what are our molecular interactions? Usually they're attractive, causing materials to cling together. Okay? Two types of attraction that we have: cohesion, That's the attractive forces between like molecules. Water is very cohesive, okay? Water molecules tend to hang together really strongly because water, H2O, is the lightest liquid I know of. There may be some that are a little lighter, but not many, because H is 1 molecular weight, so you got 2 of those, that would be 2. Oxygen has a molecular weight of 16. That gives you a molecular weight of 18 to be water, and yet water is normally a liquid at normal temperatures and pressure. Easy to make it into a gas, but you have to add heat to do that. So water really is a strong cohesive material. Adhesion, on the other hand, are attractive forces between unlike molecules. Think of adhesive tape. You're taking tape, sticking it to paper, okay? Attraction between unlike molecules. Now, when you wet your skin tends to be a little on the oily side. And sometimes if you just try to wash your hands just with water, you're not going to get them very clean, especially if you've been dealing with something that's sort of oily, like motor oil or something like that. But if you put another material in there, like a surfactant, soap, that then enables the water to wet your skin even better. Now, going the other way, your glue mechanism, those are called adhesives. That's what sticks unlike materials together. Now, you can have repulsive materials. Most of them are usually attractive. Some of them are repulsive. Interactions can also be repulsive. And this would be those things that don't mix well. For instance, if you really are proud of that car and taking really good care of it, you wash it and you wax it. What does waxing do? It keeps the water from getting to the metal. So it keeps that car shiny and good looking for longer, okay? Keeps down the possibility of rusting and stuff like that, because water and oil don't mix, okay? They will beat up on one another. B-E-A-D, not B-E-A-T. Beat up on one another, okay? That's going on the molecular level. A lot of times molecules are attractive, but occasionally they are repulsive, and it won't advance. All right, now moving on to page 89. Okay, we're going to look at what they call the phases of matter. In the old days, they used to call these the states of matter. Okay, however, when quantum mechanics came into play, they had another name, or they used the concept of states in a different context. So they now call these phases of matter. The first phase we'll talk about are solids. What makes a solid a solid? Okay, this dresser right next to me, the door right back there, the wall, those are all solid. My headsets, okay, my glasses, okay, these are all solid materials. What makes it a solid? It has a definite shape and a definite volume. Okay, now it can vary a little bit with swelling and shrinking, but it's very minor. Okay, definite shape, definite volume. Where does that come from? It comes from a rigid three-dimensional structure of the material. Okay, the wood, the masonry that's on the wall, the plastic that's in the headset, the whatever you're dealing with, the computer here, okay, it has a definite shape, rigid three-dimensional structure. The atoms and the molecules are fixed in place. They don't do a lot of movement around. They do have a little bit of motion. Like I said before, all atoms, all molecules are always moving, but they're very restricted in their motion, basically just vibrating in place. That's all they do. They can't move around past each other, so they just vibrate, okay? And that's all they do. That's what makes a solid a solid. Okay? This illustrates this. This is in 2 dimensions, but you can imagine it in 3 dimensions. And they're not really springs, but you can imagine this is sort of a model that we have. Okay? That the molecules just are fixed in place, and all they can do is vibrate around each other. Now, why is this important? Okay? Because when you start heating something up, the vibrations, remember we're talking about the microscopic versus macroscopic. On the microscopic level, when you heat something up, you make the vibrations happen more rapidly. And when they happen more rapidly, they tend to expand just a little bit. And you know that's true. The metal on railroad tracks, if you were to place those down there in the coldest part of winter, jam them up against each other, and trying to have the least amount of crack between the tracks, and then in the summertime, it's going to warp. It has to, because in the summertime, the hotter temperature makes it swell even just a little bit, okay? And you will actually warp the tracks because it will expand. So when you heat things up, the vibration happens more rapidly, okay? Now, that has to do with heat, okay? Now, how do you go from a solid to a liquid? Think of some solids. How do you make them become liquids? What would be something you could do to them? I've already hit it several times. Exactly. Exactly. You got it right on the nose, okay? When you add heat or energy of any time to a solid material, you can, now not all solids will do this, but a lot of them will, they become liquids. Why? Because that vibration increases until you break that chemical bond, and now the individual molecules are free to pass each other. They're no longer in that rigid three-dimensional structure. They are now broken free. You added energy, broke those chemical bonds that held them together. Okay? These atoms and molecules bonded in place, they now break. So to become a liquid, then, you still have a definite volume because the molecules tend to stick close to each other, proximity, but they're no longer fixed in position, so they take whatever the shape of the container. An indefinite shape, but a definite volume. Here you have only weak cohesive bonds between the component molecules, but not rigid bonds like you did in the three-dimensional structure, but weak cohesive bonds which hold them close to each other. Now, the constituent molecules are mostly in contact with each other, being held in proximity to each other, but not in fixed positions. Fixed positions are solids, proximity are liquid. Now your allowed motions are vibrations. You still have those, but now you can rotate past each other. Limited translation, but it does have some translation. That's what makes a liquid a liquid. And now the molecules are broken apart and they're free to rotate, vibrate, and in a little bit of way translate. Okay? Limited translation. But they stay close to each other. Proximity, giving them a definite volume but no definite shape. That's a liquid. Now, what's the next phase of matter? A gas. How do you get a liquid to become a gas? Any ideas? Further heating it, absolutely. Add more energy. And what happens then, you break that proximity bond that holds them in place, and now the molecules are free to go wherever they want to. They're no longer being held together. Just like you heat water and it becomes water vapor. Okay? That's exactly what's going on. So you take the definite volume, indefinite shape, add more energy to it, and you get gases. Indefinite volume, indefinite shape. I mean, there's no fixed volume. Now, if we were in a classroom, I wish we were, but we're not, and I were to have snuck in there ahead of time and put a bottle of ammonia down in one corner where nobody would really notice it, okay? And then I said, well, I have to go back to my office for something, but right before I left, I opened that bottle of ammonia, okay? And then I left the room, mean person that I am, okay? At first, the people sitting pretty close to that ammonia are going to start noticing, oh my goodness, what's that smell? And soon the whole room, and y'all probably would have left before I got back there, because the ammonia permeates throughout the room. No definite volume, no definite shape. That ammonia gas is escaping and filling every corner of the room. It starts near where the ammonia is, but ultimately would be the whole thing. That's why ladies and guys too who wear colognes or perfumes, you know, if they got a bit too much on them, they'll fill the entire space. You know, you can tell, whoa, they got a lot on, don't they? Okay, so that's gases. Okay, the allowed motion now are vibrations, of course, rotation certainly, but free to translate and go anywhere they want to. Mostly random, mostly free paths. They just take off and go. And this is what it looks like then. Nothing's holding these molecules together. They will occasionally bounce into each other, but then they bounce right away. They don't tend to hang together at all. They just fill the entire space. That's the phase of gas. Now, are those your only three phases of matter? It's the only three the book talks about, but there is a fourth one. Does anyone know what that fourth one is? Plasma, absolutely. How do you think you go from a gas to a plasma? Put more energy to it. You're absolutely right. Now, the light bulb that used to be in this room right here was a complex fluorescent bulb tube, you know, one of those that are curled around. It went out a few months ago, and I put a LED in place, so it's going to last even longer. But when it was a complex fluorescent, I would have then said we have a plasma in the room. We don't really now, but we did then. What is a plasma? That's when you add more energy to a gas, so now you're either knocked off electrons off the gas or attracted electron to a gas. So now you don't have atoms anymore, you have ions. An ion is a charged gas, okay, a charged atom or molecule. Either has excess electrons or a deficit of electrons. Excess electrons is a positively charged ion. Excess of electrons would be a negatively charged ion. A deficit of electrons would be a positive charged ion. Okay? Think back to that sodium and chlorine. Sodium tends to lose electrons easily. Chlorine tends to hug them, you know, hang on to them. So what happens? Sodium will lose an electron, become positively charged. Chlorine will pick up an electron, becomes negatively charged, and then they're attracted to each other because one's positive and one negative, and unlike charges attract each other. That's what holds your table salt together. That's what makes your the strong bond that you have between sodium and chlorine. Okay, so let's get back to plasmas. You've either added enough energy to knock off electrons or to pick up electrons. That fluorescent tube that had, if you ever noticed a fluorescent tube at a light fixture, the long ones are the fluorescent ones, they always have a pretty big base somewhere in there, and that's a very strong capacitor. That very strong capacitor is either what's going to knock off or supply extra electrons. Knock them off or supply them. And then those gases are no longer gases, they are plasma racing back and forth the length of those tubes, and as they go, if you've ever seen a broken fluorescent tube, it has that white powder inside. Okay, that white powder is a phosphorescent material, which means that when it is energized by rapidly moving plasma or charged particles rapidly moving up and down the tube, it makes the electrons in that plasma jump up an energy level. And then when the energy passes, it falls back down an energy level. Well, that falling down then emits a photon of light. That certain distance in that process there produces a light. And that's why certain materials will produce white light. Some of them will be yellowish light, some of them will be reddish lights or bluish lights or whatever, depending on the powder that's inside that tube. So that's what you've got with a plasma. Add more energy and you wind up with plasma. Now here's a question, not in your book, not on the slide set. In the universe, what do you think the primary phase of matter is? Is it solid? Is it liquid? Is it gas? Or is it plasma? Or a good mixture of all? Or have no clue?
Next question again.
Okay. In the universe, what is the predominant phase of matter? Solid, liquid, gas, or plasma?
Liquid.
Okay. On the surface of the earth, you'd be absolutely right, because most of the surface of the earth is covered with water. Miles of water, depth of water. But that's not the whole universe. Next.
Combination then.
Okay, of which? Which would be predominant?
Solid and liquid.
Okay.
Solid is kind of gas, actually.
Yeah, okay. You're living on the surface of the earth and it shows, okay? Because most of the material of the earth is solid. You know, the rocks, the sands, the soils, all those kinds of things are solid. Your liquids, your waters and stuff are liquid. And then we're surrounded with the atmosphere, which is mostly gas, But guess what? We're just a little planet in a big, big universe. What is most of our solar system? The sun. Remember? Something like, I can't remember what the percentage is. Something like 800 times the mass of the entire solar system is in the sun. Okay? Huge, huge portion is all of the sun. And what's the sun made up of? Mostly plasma. And then you go to bigger stars, even more. Most of everything we understand is plasma, except we don't understand dark matter and dark energy. Dark energy is probably plasma, but dark matter, we don't even understand it. It's probably not plasma. So it is a mixture, but I bet you most of the universe is a plasma, not a solid, liquid, or a gas. But that's just a guess on my part as well. Okay, we're only going as far as gases. So let's now move to what they call molecular motion. Okay, we got 5 minutes. Let's see how far we can get. We're over here on page 90. Table 4.1 is a pretty good little table. It's pretty simple. I'll let you take a look at that. Molecules move. I said it before, I'll say it again. Molecules and atoms are never still. Never, ever, ever still. No matter how cold they are or anything else, they're always moving. Even those tiny little vibrations, they're always moving. Now, this is characterized by the average kinetic energy of a large sample. Okay? If everything's always in motion, that means everything has a certain amount of kinetic energy, because kinetic energy is the energy of motion. Okay? The average kinetic energy in a large sample, that's basically how we define temperature. Temperature is the measure of the average kinetic energy on the molecules making up a substance. Okay? An incredibly slow moving vibration and stuff is going to be an incredibly cold piece of material, but it always has motion. So temperature is proportional to the average kinetic energy of the constituent molecules in a material. So even though we said thermodynamics is dealing with macroscopic concepts, it all gets down to what's happening on the molecular level, and the average kinetic energy of those molecules, that is what temperature is proportional to. Now, let's go back to that ammonia that I opened the bottle. Remember how bad it smelled? What if I had put a little Bunsen burner under that? Then the gases would have diffused much more quickly at higher and higher temperatures. Now, I wouldn't have done that because I'd be afraid maybe something would explode, but that would have sped up the process. When my wife, I don't think she's here yet, but when she does come, if she puts starts something cooking in the kitchen, I'm going to smell it pretty soon, because as you start cooking something, the gases diffuse more quickly. Boy, that garlic, that onion, whatever it is, you'll smell it much more quickly. You also have, even in solids and liquids, when you heat up something, it expands. Sometimes it's very little, but it expands. When you cool it, it contracts. And like I was talking about before, you have to have those expansion joints in your railroad tracks and just about everything. The concrete on the expressways. If you've ever gone over a bridge, you know it's a bump, you know, as you go over. They have to have those expansion joints there, because in the summertime it's going to expand, and if you didn't allow for the expansion, you have buckling of your highway, buckling of the railroad tracks. Okay. In gases, they are even more to diffuse at higher temperatures. I think I told this story before. A kid that I was doing a few things with when I was living in Nebraska, he left the basketball out overnight, and it was cold in the wintertime. And when he went to pick up his basketball, he said, "Oh man, it had sprung a leak." I said, "Nah, just take it in the house." He said, "No, it's flat. I need to pump it up." I said, "Just take it in the house." And we left it there for about an hour. I said, "Go get the basketball." He said, "You forgot. It's flat." I said, "Go get the basketball." He went in to get it, popped right back. I mean, because at colder temperatures, the gas molecules don't move as quickly, and so they don't bounce as hard, less pressure. Move it in the house where it maybe to 70 degrees, where outside it was 40 degrees, then suddenly the basketball has all the pressure you need. Okay, that happens with liquids, it happens with solids, it happens with gases. There's one sort of exception to that, and that's our good old favorite liquid, water. Okay, water, when it gets colder, only in a very small range, from 4 degrees Celsius down to 0 degrees Celsius. That would be about 40 degrees Fahrenheit to about 32 degrees Fahrenheit, something close to that range. Okay, water actually expands when it cools. For that very small 4-degree range, it expands when it cools. That's why ice floats. If you have a glass of ice water there, the ice will be floating on top, the cold water underneath. Only material on the planet that happens. Okay, water is such an unusual, though it's ubiquitous material. Has these and if it weren't for that, life on this planet would not exist, because otherwise, in very cold climates, your rivers, your lakes, your ponds would freeze from the bottom up rather than freeze at the top and leaving water underneath for animals and plant material to keep living. Okay, those are your molecular motions. Molecules are always moving, and I think we've just gone past our time limit here. Let me go cover this one slide here. This is a distribution of molecular speeds at different room temperatures. The average molecular speed in meters per second. If you heat up this gas, okay, then this hump moves further in the right-hand direction, because the average molecular speed increases. That is how they define and have made note that temperature does depend on the average kinetic energy of those molecules. You cool this off and the peak moves down this way. Okay, heat it up and the peak moves in that direction. That indicates that the higher kinetic energy goes with the higher temperature. Okay, now we will begin next time with 4.2, which is temperature, on page 91. Let me see if I have any marks on the page. I don't believe I do. So we'll begin right there. Now, do y'all want to take a quick break before we get started on the lab today? Yay or nay? Okay, let's take a quick break. What I'm going to do is right now I'm going to pause the record. All right, I'm back, and let me see if I can find my... Nope, I don't know where it's gone. Okay. Let me close this. Uh-oh, I don't know what it's doing now. Driver update. I have no idea what that's doing. Okay. I don't know, it's something to do with my board here. So I'm going to minimize this. Okay. I don't know what it's doing. Okay. Okay. I'm going to try it one more time here. Okay. All right. I had all this open before class and now it's lost it all, or I don't know what it does with it. It still was there, but it won't access it. All right, I believe we're on lab 6 now, aren't we? We had lab 1 the first week, 2 and 3 the next week, 4 and 5 last week, so I think we're on lab 6. Okay, all right. Now, I don't know what this new icon is down here. I don't know what that's doing, but I'm going to tell it to do it.